All right, hello everybody. We're going to talk today about what we call the ideal gas law. If you take a look at the gas law that's written down below, it should look a little bit familiar, but there's two new important parts. Notice the N is stands for numbers of moles, and the gas constant is R. Oh, and let me say, I'm going to talk kind of quiet today because my family is still asleep. I got up kind of early, and I might wake them up while I'm doing the screencast, and they would be mad at me. Okay, so let's do actually a quick review just to remind you real quickly. Kinetic theory of molecules or kinetic theory of gases, what that is. We talked about that in the phase change notes. So it's just the basic idea is that molecules are always in motion. Molecules of a solid are in less motion. Molecules of a gas have enormous motion. And that's totally relevant for our gas unit. So this whole idea that the molecules are in motion, that's kinetic theory. Then we talked about four or five different gas laws already. And the one that everybody forgets is Graham's law. Like I forget about it. It's not that I forget what it is. Graham's law, it gives us information about how fast the gas effuses. That was a word we learned, which just meant that it passes through tiny holes, like out of a balloon, for example. How does helium get out of a balloon? It's passing through the tiny holes of the latex balloon. That was an example. So we learned that the rates are inversely or related opposite of their masses. So if you have the rate of gas A, then you put the molar mass of it down below. And if you have the rate of mass B on the bottom, you put its mass on the top and then take the square root of it. So Graham's law, we don't use that a whole lot, but that was just one we had talked about a while ago. And then we did several labs. We did a lab with Boyle's law, PV1, P1V1 equals P2V2. We did a lab on Charles' law, V1 over V1 over T1 equals V2 over T2. And then we did Gay-Lussac's law, which is pressure over temperature equals pressure over temperature. Finally, we took all three of the Boyles, Charles, and Gay-Lussac's and we put them into one, PV over T equals PV over T. And that, if you just remember that one, Graham's law is separate, but if you remember the combined, you can use it to solve any of the other kinds of problems. So now we're going to talk about what's called the ideal gas law. And the first thing I'm going to tell you is what does it mean by ideal? So the equation only holds true if the gas is in a specific circumstance. So it has to be behaving ideally. And that means that the molecules are not attracted to one another. We assume that that they're so far apart from each other that they're not experiencing intermolecular forces. And that when they collide, no energy is lost. They are perfectly elastic collisions. They crash into each other and bounce off. That's never actually 100% true, but it's negligible. And so we can ignore that fact for the ideal gas law as long as the gas is at a reasonable temperature, pressure, or volume. The moment that we start going to extremes of temperature, pressure, or volume, and I'm not going to go into what those extremes are, but you can imagine, then the ideal gas law doesn't apply. These molecules are no longer, they're getting so close to each other that they're impacting, their molecular forces are impacting one another. So the ideal gas law does not apply. But let's talk about when it does apply. And that's all we're going to look at in this particular unit. Oops. So this says characteristics of any gas. Sorry that my picture is in the way. So we've learned these characteristics of all gases. We've learned temperature, and we know that we measure temperature in metrics. We measure it in in Celsius or Kelvin. For all of the gas laws, let's convert everything into Kelvin, which means adding, if you've measured in Celsius, adding 273.15 Kelvin. Remember that Kelvin doesn't use degrees, so you don't say degrees Kelvin, you just say Kelvin. Volume, we're going to be measuring in milliliters or liters. In general, convert to liters if you have milliliters. Pressure is a wacky one and should irritate all of you because you can measure it acceptably in three different units. You can measure it in millimeters of mercury. Remember that inches of mercury is not a metric system. You can measure it in atmospheres and you can measure it in kilopascals. They're all different units. And so depending on which one you're choosing with the ideal gas law, you have to do the ideal gas law a little bit differently. You're going to change your gas constant, and that'll make sense in a minute. And then this new thing we haven't talked about, we're going to call the amount of the gas, which is is the moles of gas, and it's going to use the letter N, which I always found as a student a little bit irritating. But the reason they can't use the letter M is that that's already taken by meters. So it is the letter N in this gas constant. I'm sorry, in this ideal gas equation. So now, if it says down at the bottom, if we know 3 of the 4 characteristics, the ideal gas law allows us to calculate the 4th characteristic. So here's how you would do that. I'm going to show you just how to rearrange simple algebra. It's the same thing you should have been doing with the combined gas law already. So let's say, for example, that we know the pressure, the volume, and the temperature of a particular gas, but we don't know how much. We don't know the moles of that gas. We're going to rearrange to solve for N. And I will just say down at the bottom, it says, remember, R is a gas constant. That means it's the same in every ideal gas equation, depending on the units. And we'll explain that. So we'll go more into R in just a moment. But for the moment, just accept R is, and you don't need to know anything more than that. So let's isolate N. We're going to try to solve for N. So if we divide both sides by R, you can see that the RTs would cancel each other out, and you would be left by N by itself. So your rearranged equation is now PV over RT equals N, and now you can solve for moles. Here's another example. If you know the number of moles and you know the volume and the temperature, but you don't know the pressure, you can rearrange again doing the same kind of algebra. Divide both sides by V. The V's on the left side would cancel each other out, and you would be left with P standing all alone. So P equals nRT over V. So as long as you know the ideal gas law is PV equals nRT, you can solve for any of the variables. So I guess I have to move this. Okay, so it says, so what is R and where does R come from? So R is based on Avogadro's law, which we mentioned once before, but we're going to mention it again here because nobody remembers it. So Avogadro's law says that at standard temperature and pressure, that's STP, and just to remind you what STP is, that's 1 atmosphere of pressure and 0 degrees Celsius, or 273.15 Kelvin. Avogadro's law says at STP, 1 mole of any gas takes up 22.4 liters. So do you remember your mole roadmap? It looked like this. It had 3 arms to it. The third arm we never used in the moles unit, and that was because you didn't know anything about gases. Well, now you know something about gases. So that third arm was a conversion factor between moles of gas and liters of gas. And so if you every gas at STP takes up 22.4 liters of space, and so that's how you can do conversions. We'll get to that. So now watch what Avogadro does. We can take all that information. We have pressure, we have temperature, we have moles, and we have liters. We can put those into this equation and solve for R. So PV over NT equals R. So if we put those things, those from Avogadro's law, we put 1 atmosphere times, so pressure is 1 atmosphere from this Avogadro's law right here. I don't like it when that pops up. Go away. Okay, well, it popped up and I couldn't make it go away. But 22.4 liters over 1 mole times 273, and that should say 273.15 Kelvin, equals R, which is the gas constant. And if you add that all up or multiply it all out, you should get 0.0821. Now look at the wacky units on this gas constant. Liters times atmospheres over Kelvin times moles. Those units are wickedly important, and it's going to change if your units are different. So the first question should be, well, you said I could use different pressures, KJ. What if I choose to measure my pressure in millimeters of mercury? Well, if you do that, you have to change the gas constant. So the gas constant changes. Okay. Things that are constant aren't supposed to change. That was my humor there. So there are 3 gas constants that we can work with, primarily 3 gas constants that we're going to work with. You could use 0.0821 if you're measuring pressure in atmospheres. You could do 62.4 if you're measuring pressure in millimeters of mercury. And of course, kilopascals would be 8.31. And that's the gas constant depending on which pressure you're using. All right, so let's try an example. Move my picture out of the way again. Actually moving up in the corner. So let's say we have argon gas. It's in a light bulb and it has a temperature of 85 degrees Celsius. Right away, I notice that it's not in Kelvin. I'm going to have to convert that. And it has a pressure of 1.48 atmospheres. Ooh, that's a unit I can use. If the bulb contains 1.25 grams of the gas, what is the volume of the bulb? Hmm, grams isn't really part of this equation, so that tells me I'm going to have to do some converting. If I know it's argon and I know I have 1.25 grams, I can use my mole roadmap to go from moles to grams, which was down at the bottom. And you've done this with stoichiometry, and you've done this lots of times before. So we're going to do a few conversions, and then we're going to plug it into the ideal gas law. So the first thing we did here is we converted N. We needed to figure out what N would be. So they gave us 1.25 grams of argon. How many moles of argon is that? That's the mole roadmap. You've done that with stoichiometry before. So you multiply it by its conversion factor. 1 mole of argon is the same as 39.9 grams of argon. Notice that in the last unit, when we did stoichiometry and we went from grams to moles, we were going from grams to moles of a different element or a different compound. This time we're going from grams to moles of the same compound. So this is just a one-step conversion. We don't need that mole to mole ratio because we're not comparing two different gases or two different elements or two different compounds. We're comparing the same, I'm not comparing, we're just converting one from grams to moles. So it's just a one step. For pressure, we don't have to do any converting. For Celsius, we do. We need to add that 273.15 to convert it into Kelvin. And then we plug all of that into our ideal gas law, solve for V, so isolate V, and we get that V would be 0.622 liters. And notice that it has been converted into sig figs. All right, another important use of the ideal gas law, we'll talk about that. It can also be used to find the molar mass of a gas, and that's useful for finding the identity of an unknown gas. So how do we do that? So let's say scientists are studying a gas and they're like, what is this gas? You can use the ideal gas law to figure that out. So we start out moles. This is a little bit confusing, so just pay attention for a moment. Moles can be written as grams of a sample over its molar mass. Pause, let that sink in. Let me back up for just a second, make sure you see that. Okay, so N is moles again, remember? So here's the grams of the gas times 1 mole of the gas over the molar mass of the gas. Now, if I were to write that more efficiently, I'm not always thinking more efficiently is a good idea. I'm somebody who likes to write it all out so my brain doesn't get confused. But if I were to write it more efficiently, 1 mole of argon, you don't need to include that in your equation because it's just the number 1. So technically, when you do this math here, you're just doing 1.25 times 1 over 39.9. So you could throw out the 1 and you could just do it 1.25 divided by 39.9. And that's what they're doing in the 2 slides from now. They're doing the grams that you're given, the grams of the gas over its molar mass, and that gives you N. They just didn't bother to write the 1 mole of the gas. So here it is again. Moles, N, is the grams of the sample. It was grams of argon in our example. And then over the molar mass of argon, that tells you how many moles. So you can write it, you can write N in a different manner is what they're trying to show you. So PV equals nRT. So if we replace N with grams over molar mass, you can rewrite the equation as PV equals grams of RT over the grams of RT. I didn't say that right. Grams times R and T over the molar mass. That's another way of rewriting this particular equation. So now let's try doing this in a sample problem. So I'm going to lower this again, sorry. I pulled this example right off the internet. This is a link, so if you're ever looking at this presentation yourself, it'll take you right to the video that talks about it. It was an easy problem, so I thought that I'd go with it. So it says at 137 degrees Celsius, we need to convert to Kelvin, and under a pressure of 3.11 atmospheres, a 276 gram sample of an unknown, noble gas occupies 13.46 liters of space. What is the gas? Now, let me say a couple of things really quickly because I didn't say that on this page. You can use this to determine the identity of a gas. You can use the ideal gas law. However, it is a little bit more complicated than I make it sound. So let's say you find out that the molar mass of the gas is 18. I'm sorry. Let's say you find out the molar mass of the gas is 18. That's a good one. So you look on your handy dandy periodic table and you see, oh, fluorine has a mass of approximately 18. It's actually 19, but we'll say it's approximately 18. So your guess might be, oh, this gas must be fluorine gas. Well, that would be completely wrong. Fluorine gas is diatomic, which means it's always F2. And so it would never have a mass of 18. It would always have a mass times 2 of that. So the thing that would actually have a mass of 18 is water. 2 hydrogens plus an oxygen gives you a mass of approximately 18. So it's not a gimme that you can figure out the gas, but it gives scientists information. Okay, the molar mass is 18. There's only so many things that it could be. Let's start figuring out what it could be. For your circumstances, when you do problems for me, I have to give you some hints about the gas. Like I would have to say it's a diatomic molecule, or I'd have to say it's a noble gas molecule. That didn't make sense. It's one of the noble gases, to give you a little bit of a hint so that you could whittle down what are the possible answers for that problem. So just so you know that. So this one tells us specifically it's a noble gas. So we know it's one of the, oops, can't point there. It's hard to do it on the camera. So it's one of these gases here. So now we just have to see which one the math correlates to. So it says, already read it. So what is the gas? So let's go ahead and see what we need to do for this one. I'm in the way again. I'm always in the way, you guys. So we're going to rearrange the PV equals nRT to be PV over RT equals N. And we're going to solve for the moles of the gas so that we can then solve for the molar mass of the gas. And then we can look up the molar mass on our table, look at all the noble gases and see which one has that molar mass. So first, let's solve for moles. They didn't give us moles. This information right now, the 276 grams, that's extra information that you're not going to use right now. You're going to use it in the next step. Okay, so PV over RT equals N. So, oh, I screwed up the formatting on this. Give me just a second. I'm going to make it look nicer. It'll take my computer just a moment. Let's see if we can open up the text box a little bit. There we go. To make it look nicer. Give me a moment because that'll help you, I think, if I do it right. All right, there we go. So, there we go. So now we're putting the pressure. The pressure was 3.11 atmospheres. There's P. Here's the volume, 13.46 liters. There's V. R is the gas constant, and we measured pressure in atmosphere, so I'm going to use the gas constant that was 0.0821. That is a number you need to write down and have handy for your tests, so make sure that you know your gas constants. And then temperature, we've converted into Kelvin, so 410.15 Kelvin. Calculate that all out and you find out that we had 1.24 moles. So now we're trying to figure out what is the molar mass of this gas. So let me back up for a second. Remind you right here, we said moles can be rewritten as grams of the sample. Oh yeah, they gave that in the problem over the molar mass. So now we're going to solve for the molar mass. So we figured out, we figured out moles. So now we're going to rearrange that. 276 grams divided by 1.24 moles tells us that we have the molar mass is going to be 222.6 grams per mole. Let's see if we can do that again. I don't think I said it very clearly. So let me back up. Watch how I back up. Moles is equal to the grams of the sample divided by the molar mass. So we would say N equals grams of the sample over the molar mass. We know the grams of the sample and we know the moles. What we don't know is the molar mass. So let's get molar mass isolated all by itself. So in order to isolate it by itself, to do that algebra, see if you can do it in your head here, I would multiply both sides by molar mass. If I multiply the right side by molar mass, it makes it disappear from the bottom, and it brings it over to this side. So I have molar mass times N divided by grams of sample. Now I'm going to divide both sides by moles, by N, and I'm going to have grams of the sample over moles. So now let's take a look. Grams of the sample divided by moles equals my molar mass. So we solved in this equation, we solved that the molar mass is 222.6. So now we want to know the identity of the gas. We were told it was a noble gas, so we look it up on the periodic table, and way over here, the atomic mass, or the molar mass of radon is 222 point something or other. It's never exactly right. And so we know that our gas is radon. So that's how we would solve a problem like that. All right. And then one more thing I will mention, we can also use the ideal gas law to solve problems to solve the identity using density. So I'm not going to give you an example problem on that, but I'm just going to show you how to do it. So here's our rearranged ideal gas law. PV equals N. And remember we said N is grams over molar mass times RT. So that's our rearranged equation. So now we're going to rearrange it again. Oh, how annoying, KG. My head's going to explode. So let's get molar mass all by itself. So I'm going to multiply the right side by molar mass. I'm going to multiply the left side by molar mass. When I do that, it makes the molar mass go away on the bottom, and now it's on the left side of the equation. Now I'm going to divide the left side of the equation by PV, and I'm going to divide the right side of the equation by PV, and so we get PV on the bottom. So molar mass is the same as the grams of the gas times the gas law times the temperature it's at times the pressure and volume that it's at. It turns out that grams over volume, this part right here, is the same as density. So we can actually substitute density into this equation, and you're going to need to write this equation down. The molar mass equals density times the gas law times temperature over volume. Temperature in Kelvin, I'm sorry, over pressure. I said that wrong. And then pressure is going to vary depending on which gas constant you're using. Or you could say the gas constant is going to vary depending on which pressure you're using. But you can use density to then figure out anything. And so I might give you in a problem, I might say, well, the density is blah, blah, blah. And then you plug it in and rearrange it as you need to figure out any of the other variables. But I'm not going to solve one of those problems right now because I've rambled on long enough. So good luck. You have a worksheet to work on. Let me know if you have any questions. Bye-bye.